we are going to cover the big ideas for section 3.2. So we're going to be predicting using regression lines in 3.2 using this equation. So we have y hat, so we're predicting y. And then we have a plus bx. A is your y-intercept, and b is your slope. So your slope is b. And here's how we're going to interpret slope. So with each additional whatever your x variable is, the predicted whatever your y variable is in context of the problem will either increase or decrease by your slope. So the underlined parts are what you should be filling in when you're talking about slope, when you're interpreting it. Then the y-intercept, your a, when x equals 0, but use context of the problem. Don't just say x. Use whatever that variable is. The predicted y is whatever the y-intercept is. So when we're predicting using regression lines, what we have is a set of points when then we're trying to put a line in there that best fits the data. So we're going to predict values using the line. So as you see, data points are the red. If I wanted to predict, let's say this was at 50, whatever it is for x, the line would give me a prediction at 50. Sometimes the points are closer to the line, sometimes they're further away. So we're predicting using this line. If we wanted to predict at like 100, we could take a guess at what was out there. Interpolation is predicting inside. Our data set, so our data set is there, so like predicting at 50, what y would be interpolation. Predicting at 100 is extrapolation, so predicting outside. Residuals. So when we're using the line to predict, and we predict a value that's there, the residual is the distance from the actual point straight down to the predicted point. So the easy way to remember that, residual is actual point minus predicted. So you take the actual data point, subtract what the line would predict to get to your residual. So what this is, meaning in the context of the problem, is the actual y in the context of the problem was whatever distance that residual is higher or lower than the prediction for x equals whatever number we were predicting with. So residual actual distance minus the predicted distance from the line. With a residual plot, that's when you graph the x, so your regular x variable, versus then your residual. So your residuals come in to be your y's instead of your y variable. So with a residual plot, what you want, if the data is linear, would be like random scatter. Something like this. Just random above and below, no sort of pattern there. It's bad if you see a pattern. So some patterns you might see is the points looking like that, or getting more spread out as x gets bigger. So those are two patterns to look for. If those patterns are there, that is not good. So we want no pattern. Then the standard deviation of the residuals is just as it sounds. The variable we use to represent that is s. So what the standard deviation of the residuals means is the actual whatever your y variable is in context of the problem is typically about whatever your s comes out to be away from the number predicted using the least squares regression line. So basically it's the average distance the predictions are from the line. Or sorry, the actual points are from the line. The coefficient of determination is r squared. So remember, r is your correlation coefficient. Tells you how close the points are to the line and the slope. Now since we're squaring r, this will no longer tell you if the slope is positive or negative. What it does tell us is about whatever r squared is percent of the variability in your y variable is accounted for by the least squares regression line. So when we're predicting something, it tells us the percent of the variability in our variable that can be accounted for when we're using the least squares regression line. So the least squares regression line is the line that your calculator will come up for you with automatically. And what it does, what it means, is if we take the residual and we square it, we do that with all of them. The area of those squares is minimized. So your calculator automatically puts the line in there that minimizes the area of those squares. So we want our least squares regression line to have a low standard deviation of the residuals, low s, and a high r squared, which means then our correlation, or r value, is close to either 1 or -1. Also, just a little fun fact of the day, the average of the y's would be somewhere about there, and the average of the x's would be about there. So if you took the average of the x's and then the average of the y's separately, the least squares regression line will always go through that. That point right there is called the mean point. So your least squares regression line will always go through the mean point. So normally we'll find the least squares regression line just using our calculator. If you ever need to find it by hand, the y-intercept and the slope are represented on your formula packet for the AP exam using these two. To find the slope, you're going to take your correlation coefficient r times the standard deviation of the y's over the standard deviation of the x's. If you need to find the y-intercept by hand, you can take the average of the y's, subtract off the slope times the average of the x's. But almost all the time we're going to just find it using the calculator.